Hello everyone, I am Guru Özen. This is joint work with Michael Wolf. We are both from NVIDIA, and today we are going to talk about Performant and portable OpenMP. OpenMP started as a shared memory parallel programming model. It provided a directive that is very simple to understand and powerful. And this is OMP parallel do or OMP parallel for. And after that, all the programmer has to do is to identify the parallelism on the loops and put this directive above the loop. And in the end, programmer got a good performance quickly without changing the code itself. So code remains portable and performance is also portable. And all in all, this model on multicore is a great success. And computer architecture has advanced a lot in recent years. Vectorizations, multicores becomes mainstream. Plus, we got accelerators, especially GPUs, and these devices came with the multidimensional parallelism. OpenMP followed the prescriptive policy and added a new directive for each level of parallelism to accommodate all these new architectures. Here I am displaying a table in the upper left corner. It shows parallelism mappings of the OpenMP accelerator model's directives. Well, for teams, you can think that it enables CUDA thread blocks. And for the parallel, it enables threads on the CPU and GPU. And for the SIMD, it is enabling the vectorizations. Now, the big question of OpenMP programmer is how to use this directive to map parallelism. And I will demonstrate this issue with the code we have on the screen. And first, I'm going to start putting all of these new directives naively on the outer loop, just like parallel do. Okay, here is my mapping. Now let's stop a minute and think, how does this code maps in the architecture considering the performance? Well, for multicore, it is not very great because I am not vectorizing the inner loop. My SIMD directive is on the outer loop. And for GPU, the performance is even worse because the optimal memory access in GPU is coalesced access, and that is adjacent threads accessing consecutive memory addresses. And therefore, assigning thread parallelism here is a crucial task and directly affects the performance. Here, parallel directive that manages the thread parallelism is on the outer loop, so that is wrong. And now let's get the performance a little bit, and I am moving the SIMD directive to the inner loop for the vectorization. And I think I got the performance I desired or deserved and from the multicore. From the GPU, my performance is still very bad. Now, to make my GPU happy, I am going to move the parallel directive to the inner loop. And it gives me finally coalesced memory access and good performance. But what happened for the multicore now? I completely ruined the performance because I put the parallel directive inside the loop, so it does fork join all the time. It is a big overhead. And as you can see, even with a simple code, it is so hard to write performance portable code with OpenMP today. And then you might be asking, and how these people is using today? OpenMP has been around for a long time. Well, it's a good question. To answer that, we went and looked at the SPEC ACCEL benchmark suite. And we have seen that benchmark authors used macros. It's disappointing indeed, but we understand very well why this happens. It is not clear whether this directive is good or bad. And its name might be even different from architecture to architecture, even from compiler to compiler. And no need to mention here, if you are controlling your program with macros, you will need multiple binaries. So to overcome performance portability problem, we are proposing a fully descriptive OpenMP. And in this model, user tells the compiler what to parallelize rather than how to. And we leverage OMP loop directive, which is already in the OpenMP standard. However, we extend its capabilities. We use this directive because it means the following iterations are data independent. So the compiler we develop can automatically create the parallelism and map these loops to the beneficial level of parallelism automatically for each device separately. And in the end, in the single binary, you have a performant code for multicore and GPU. And also, we make sure that this model is fully compatible with SPMD execution model. This is the execution model of GPU. It wasn't the case for prescriptive OpenMP model. We discussed this in detail in our article. For more information, I recommend you to look on our article. And also I would like to underline that for a programmer it is really easy to write the code using OMP loop. For the example, in the code on screen we replace all the OpenMP directives with OpenMP loop. Now let me show you how much this model simplified the entire SPEC ACCEL suite in a big picture. Here, the figure shows the number of OpenMP directives in each benchmark on the suite. And with our model, 60% fewer directives are needed. So now the programmer can go back and focus on their parallel algorithms and make them better. Now let's talk about how does compiler do the automatic parallelism mapping. Remember the steps in our first slide? Our first step is still the same. User identifies the parallelism. But the second step now goes to the compiler, the parallelism mapping. And we have the same code from SPEC ACCEL and the previous slide, but I took the only first loop. Now let's start with the GPU mapping. First, compiler maps the outer loop to the CUDA thread blocks. It always does that unless these loops are data dependent. And here there might be multiple nested loops, so luckily CUDA thread blocks provides us three-dimensional parallelism, and compiler has freedom to use them all. And you might think that there is no explicit themes construct here, but it is not necessary because in our model the compiler can implicitly generate parallelism. And one compiler faces here the limit of the number of thread blocks, and they can be bigger than the loop trip count. To handle this case, compiler applies strip mining, which is a very well-known technique, and the strip size naturally maps the first or x dimension of grid. Now let's continue with the loop J, that is the second loop. Even though it is not marked with loop directive, the compiler can run dependence analyzer and figure out that it is actually parallel loop. And after this, it does two things. And the most critical mapping is the x dimension of the threads to achieve co-asked memory access. And the compiler performs stride 1 and non-stride 1 memory access analyses among the parallel loops. In this example, loop J has the most stride 1 access, so the compiler maps it to the thread parallelism. And note that this is a Fortran code. Arrays are stored in column major order. Another thing, user may accept a barrier after the thread parallelism, but in this case, loop J has no external dependence. Therefore, our compiler eliminates the redundant barrier. And the second thing the compiler does is the unrolling. To increase instruction level parallelism, it is beneficial to do. And in this example, the tiled loop TJ, is a suitable loop because it doesn't change the memory access pattern, and our compiler does that. Now let's focus on the multicore mapping. And CPU consists of multiple cores. Though this number is quite small compared to GPU, but these cores are much more powerful and they have much larger caches. And therefore, compiler usually maps the outermost loop to the threads to achieve coarse-grained parallelism. And in this case, it maps the loop K with the threads and generates static block scheduling. And for the inner loop, right now our compiler is vectorizing it. So for the performance, finally, in a single binary, I got a good performance from GPU and I also got a good performance from multicore by writing a fewer directives. Now let's look at the evaluation of this model. We used the SPEC ACCEL benchmarks and ported them to OMP loop model. And we converted all of these OpenMP directives to OMP loop. You can even do that with the grep command. Here we show two graphs. Intel host on the top and IBM host on the bottom. And the graphs show speedup against our own compiler compiling original OpenMP. And they all run on the GPU, and this is a speedup graph, so higher is better. So now looking at the geometric speedup, we see that 91% speedup on Intel and 79% speedup on IBM host. So here, in other words, our model first makes it easier to write code, and then it increases the performance. Now let's check these cases one by one. And we have two outliers where we get massive speedup. And benchmarks authors put the thread parallelism is on the wrong loop here, and that is the reason. And unfortunately, the compiler doesn't have much power in prescriptive OpenMP. And since compiler doesn't have a freedom to change this mapping that is forced by user, it led to bad performance. In our model, compiler can detect the memory patterns automatically and maps this loop to thread parallelism. and eventually we got a good speed up. And these programs, we also got remarkable speedups. This is because our model is suitable to SPMD execution. So when the compiler sees OMP loop, it can assume that this is a SPMD execution and generate a fast code. I should also mention that some part of prescriptive OpenMP are also adaptable to SPMD. And in fact, our entire SPEC ACCEL can be compiled according to SPMD model. But we are not seeing that in any other compiler. We have explained this in our article. And here is the benchmark where we are slower than other compiler. And the reason is that the optimization that ACCEL compiler is doing might be unsafe if there is a pointer aliasing. And we don't think this is detectable at the compile time, so we don't think it is a very safe optimization. And here is the case that we use a bind clause to change compiler's auto-parallelism decision. So here we agree that everything is not visible at the compile time and user's input is still valuable. And now let's look at the multicore. And here we want to underline is that performance remains the same with the less explicit directives and descriptive directives. So that was our point. And now let me conclude everything. We are proposing a performant and portable OpenMP. It is a way easier than to write prescriptive OpenMP. You just need to use OMP loop and tell the compiler what to parallelize rather than how to parallelize. And the compiler will do the automatic parallelism mapping efficiently. So you won't need macros, you won't need meta directives, and you will know that your code is always compatible with GPU's SPMD execution model. Thank you for listening.